Right now, the most expensive bottleneck in artificial intelligence isn't microchip density, it's heat. For 3 years, Washington focused almost entirely on blocking 3nm technology. But the real shift in AI hardware relies on a process using 28nm machinery equipment that's already sitting inside Chinese fabs. This is how silicon photonics and co-packaged optics are quietly changing the rules of the chip war. In March 2025, Jensen Huang walked onto the GTC stage and announced 2 new networking switches: Spectrum X Photonics, Quantum X Photonics, both built on co-packaged optics, both replacing copper interconnects with light. The CEO of the most powerful AI chip company on Earth just told the world something. Copper is dying. 1 month later, TSMC announced its COU silicon photonics integration platform had entered mass production. Broadcom confirmed Meta had tested its co-packaged optics solutions for 1 million link hours without a single failure. The entire semiconductor establishment, Nvidia, TSMC, Intel, Broadcom, confirmed the same thing simultaneously. The wire that connects AI chips together is hitting a physical wall, and the solution is light. Here is the problem with that consensus. Washington spent the last 3 years designing a sanctions regime to stop China from building advanced AI chips. It targeted ASML's extreme ultraviolet lithography machines. It targeted 3nm and 2nm semiconductor manufacturing. It targeted the smallest, most advanced, most expensive equipment in the entire chip supply chain. The entire industry just agreed on the technology that will replace copper interconnects. It does not need any of it. Silicon photonics waveguides are hundreds of nanometers wide. They are manufactured on 28nm and 45nm equipment. Equipment China already has. Equipment China is already running. This video is not about China winning the chip war. It is about whether Washington is fighting the right one. That distinction matters, because the answer changes what the next decade of AI infrastructure competition actually looks like. And it changes what policy levers are available while the window is still open. Here is what everyone agrees on. Copper interconnects inside AI clusters are reaching their physical limits. When an AI model processes 1 trillion parameters, data must move fast. Between GPU and memory, at terabits per second. Moving electrons through copper at those speeds creates 2 problems that cannot be engineered away. The first is the skin effect. At high frequencies, electrical current does not travel through the full cross-section of a copper conductor. It is pushed to the outer surface by electromagnetic induction. The effective conducting area shrinks, resistance rises, heat increases, signal integrity degrades. The second is power density. A modern AI data center running Nvidia H100 clusters spends a huge electricity share on something else, 30 to 40%, on moving data through interconnects and cooling the heat those interconnects generate. That is not a software problem or an efficiency problem. It is a physics problem. You cannot move electrons through copper at terabit speeds without generating heat. That heat is proportional to the square of the current. The heat has to go somewhere. It goes into the air, which requires cooling, which requires more electricity, which generates more heat from the cooling system. The cycle compounds. Nvidia is not quiet about this. Jensen Huang said at GTC 2025 that an era is over. The era of scaling through transistor count alone. The next scaling dimension is networking. How fast can data move between chips? How efficiently can a cluster of chips act as one coherent system? Every major player in the semiconductor industry has run the numbers and reached the same conclusion. If AI clusters continue scaling, Copper interconnects become the bottleneck that limits how powerful those clusters can be. Not the transistors, not the memory, the wire. Here is the technical escape route that everyone is building toward. Silicon photonics replaces electrical signals with optical ones. Instead of electrons moving through copper, photons move through silicon waveguides. Photons have no charge. They generate no resistive heat as they travel. They do not experience the skin effect. They can carry multiple data streams simultaneously at different wavelengths without interference between channels. The bandwidth a single optical waveguide can carry is dramatically higher than a copper trace of the same physical size. Co-packaged optics takes this concept and integrates it directly into the chip package. In a conventional server rack, electrical signals travel centimeters of copper board before reaching an optical transceiver. Even that short copper path, a few centimeters, consumes significant power. Co-packaged optics eliminates the long copper path. It places the optical engine on the same substrate as the compute chip. The electrical to optical conversion happens millimeters from the processor. The copper distance shrinks from centimeters to fractions of a millimeter. Power consumption for interconnect drops by over 70% in well-designed implementations. Nvidia's SpectrumX photonic switch uses this architecture. Broadcom's co-packaged optics solution, tested by Meta for 1 million link hours, uses this architecture. Marvell showcased custom AI accelerators with integrated co-packaged optics. That happened at the chip package level. In January 2025, TSMC's QP platform entered mass production in 2025, stacking electronic and photonic chips using three-dimensional integration. This is not future technology. It is shipping product. The question is, who manufactures the optical engines inside those products? This is not a Chinese technology. It is not an American technology. It is a physics solution to a physics problem. Every major chip designer has independently concluded it is correct. The strategic question is not who invented it. It is who can manufacture it. Now, here is where the sanctions story becomes genuinely interesting. The logic behind American export controls on semiconductor equipment is straightforward. Advanced AI chips require transistors at 3 nanometers or smaller. Making transistors at 3 nanometers requires extreme ultraviolet lithography machines. Only ASML makes extreme ultraviolet machines. Preventing China from accessing ASML's most advanced equipment prevents China from manufacturing competitive AI chips. The logic is internally consistent. The assumption it rests on is that AI compute performance scales primarily with transistor density. Smaller transistors mean more compute per chip. More compute per chip means more capable AI. That assumption was correct for the last decade of AI development. The question is whether it remains the binding constraint as AI clusters scale to millions of interconnected chips. Here is what the Yole Group analysis published in 2025 found. As AI clusters push beyond 100 terabits per second per node, something changes. The silicon-copper gap widens faster than transistor scaling. Adding more GPUs no longer scales linearly. Power and infrastructure costs rise faster than performance when the interconnect becomes the bottleneck. If the binding constraint shifts to interconnect bandwidth, the technology that matters most is not extreme ultraviolet lithography. It is co-packaged optics manufacturing. And co-packaged optics manufacturing does not require extreme ultraviolet machines. It requires 28 nanometer deep ultraviolet equipment. Equipment that China possesses. Equipment that no current American export control restricts. This is not a loophole that was deliberately created. It is a gap that was not anticipated. Because in 2021, the assumption was that AI compute would continue scaling through transistor density. Smaller transistors, more compute per chip, more capable AI. The assumption was reasonable at the time. The technology did not cooperate. The interconnect became the bottleneck before the transistor did, and the equipment that addresses the interconnect bottleneck was never part of the conversation. Here is the honest part of this story that the bullish framing misses. Co-packaged optics is genuinely difficult. The industry has been discussing it for a decade. Large-scale commercial deployment was projected for 2023, then 2025. Current projections say 2028 to 2030. The technical challenges are real and not yet solved at manufacturing scale. The first challenge is heterogeneous integration. The laser source in a co-packaged optics system cannot currently be made from silicon. Silicon is a poor light emitter due to its indirect band gap. The laser must be made from indium phosphide or another compound semiconductor. Bonding indium phosphide laser dies to silicon photonics. Chips requires extreme precision. Doing that at acceptable yields is unsolved at scale. Every major player is working on it. No one has solved it at production volume. The second challenge is yield. A co-packaged optics assembly integrates multiple heterogeneous dies on a single substrate. If any one die fails, the entire assembly may be scrapped. With expensive components from multiple sources on the same package, yield excursions have outsized cost impact. The third challenge is thermal management. Optical components are sensitive to temperature in ways that electronic components are not. A temperature shift of a few degrees Celsius can shift a laser's wavelength. Enough to degrade signal integrity. Maintaining thermal stability across a package with high-power compute chips is hard. It requires precision thermal engineering that adds cost and complexity. These are the problems that have pushed mass deployment dates from 2023 to 2028. China is working on them. So is everyone else. Here is what China is actually doing and why the scale matters. CanSemi completed a 12-inch silicon photonics production line in 2025. Covering nodes from 90 nanometers to 65 nanometers. This is not a research facility. It is a production line. The Institute of Microelectronics at the Chinese Academy of Sciences has active co-packaged optics research with direct connections to national data center procurement. Chinese state-backed investment in silicon photonics infrastructure follows the same pattern as previous materials transitions. Identify the technology that will matter in 10 years. Fund the manufacturing infrastructure now. Accept higher costs in the early years to accumulate the process knowledge that makes costs fall later. This is the same playbook as solar panels, lithium batteries, and silicon carbide. In each case, the Western analysis at the early stage was that China was subsidizing uncompetitive manufacturing. In each case, the later analysis was that China had accumulated manufacturing experience that produced structural cost advantages. The question for silicon photonics is whether the playbook runs the same way. There are reasons to think it might not. Silicon photonics manufacturing is more complex than solar cell manufacturing. The yield challenges are harder. The heterogeneous integration problem is more severe. China does not currently lead in the laser source technology that co-packaged optics requires. Indium phosphide laser production is dominated by European and American suppliers. Securing that component of the supply chain is a separate challenge from manufacturing the silicon waveguide platform. The bet is not guaranteed, but the investment is real. And 28 nanometer equipment is sufficient for the waveguide component, That part of the supply chain is already domestic. Here is the scenario that Washington's planners need to think through carefully. The current sanctions framework assumes that Chinese AI capability is limited by chip manufacturing. If China cannot make 3-nanometer chips, Chinese AI clusters cannot match American AI clusters. The framework is coherent under one condition: that compute performance scales primarily with transistor density and that interconnect is not the binding constraint. Now project forward to 2028. Co-packaged optics reaches commercial deployment at scale. AI cluster performance becomes increasingly determined by interconnect bandwidth rather than individual chip transistor count. A cluster of Chinese 14-nanometer chips can be connected by domestic co-packaged optics. It begins approaching American 3-nanometer chip cluster performance in real-world AI training. Not theoretical benchmarks. Not because the individual Chinese chips are as fast, because the interconnect advantage of optical connections partially compensates for the transistor density disadvantage of older node chips. This is not a hypothetical that requires China to win the photonics race. It only requires that optical interconnects become the binding constraint before transistor scaling does. Nvidia and TSMC are projecting exactly that transition in the 2028 to 2030 timeframe. The sanctions architecture was designed for a chip war fought on the transistor battlefield. The battlefield may be moving. Here is what it got right. The export controls on extreme ultraviolet equipment have successfully delayed Chinese progress. Progress on sub-5-nanometer semiconductor manufacturing. SMIC, China's leading foundry, has made progress on 7-nanometer production using multiple patterning with deep ultraviolet equipment. But that progress is slow, expensive, and yields lower than TSMC at comparable nodes. The controls are working on the transistor battlefield they were designed for. Here is what it got wrong. The controls did not anticipate that the most important battlefield might shift. No current American export restriction covers 28-nanometer deep ultraviolet equipment. No restriction covers silicon photonics manufacturing processes. No restriction covers the waveguide design tools that Chinese engineers use to design co-packaged optics components. The gap in the sanctions architecture is not a failure of enforcement. It is a failure of strategic foresight about which technology layer matters most in the AI infrastructure of 2030. There is still time to address this. Co-packaged optics is not commercially deployed at scale today. The delays give policymakers time to examine whether current controls cover the right technology layers. But the window is not indefinitely open. Manufacturing experience accumulates with every production line that runs. China's 12-inch silicon photonics line at CanSemi is running now. Yole Group projects silicon photonics at $5.9 billion by 2029, from $2.4 billion in 2023. Steep curve. Short timeline. And the equipment driving it is not covered by current export controls. Here is what neither side wants to say out loud. The semiconductor industry's consensus on co-packaged optics creates a strategic paradox for American policy. Every Nvidia and Broadcom announcement validating co-packaged optics validates the manufacturing pathway China is building. Nvidia's GTC 2025 announcement of photonics-based switches was not a Chinese strategic victory. It was an American company correctly identifying the direction of the technology. But correct technology identification by American companies does not automatically translate into American manufacturing dominance of that technology. Taiwan currently leads the silicon photonics supply chain. TSMC's COU platform is in mass production. Taiwan's packaging foundries are scaling. This is the more immediate competitive dynamic, not China versus America. Taiwan versus everyone else for silicon photonics manufacturing leadership. China's position in this race is not leading. It is investing to avoid being left out. CanSemi's production line, the Institute of Microelectronics Research Programs, state-backed procurement commitments. These are the investments of a country that watched what happened with solar panels and batteries, and does not want to be a late-stage buyer of technology it could have manufactured. Whether those investments produce competitive silicon photonics manufacturing by 2028 is genuinely uncertain. The bet is strategic. The outcome is not predetermined. But the stakes are clear. If China succeeds, it can build AI infrastructure that falls outside the reach of any current export control. Not because it circumvented the controls, because the technology it uses was never covered. If China does not succeed, it simply buys the optical engines instead, from Taiwan, Korea, or wherever they are manufactured cheapest, still outside the controls. Because co-packaged optics manufacturing is not currently a controlled technology anywhere. The sanctions gap exists regardless of whether China's domestic silicon photonics manufacturing succeeds. The question is only whether China is a buyer or a builder. Here is the full picture. Co-packaged optics is not a Chinese secret weapon. It is the technology direction that Nvidia, TSMC, Broadcom, and Intel have independently concluded is correct. Copper interconnects inside AI clusters are hitting physical limits that transistor scaling cannot fix. The solution is integrating optical engines directly into chip packages. This approach reduces interconnect power consumption by over 70%. It also removes the bandwidth bottleneck, limiting AI cluster scale. Silicon photonics waveguides, the core component of co-packaged optics, are manufactured on 28-nanometer equipment. They do not require extreme ultraviolet lithography. They do not require 3-nanometer nodes. They are outside the scope of current American export controls. China has a 12-inch silicon photonics production line operational at CanSemi. China has active research programs at the Chinese Academy of Sciences. China has state-backed procurement commitments that create demand for domestic silicon photonics supply chains. The challenges that remain are real and unsolved at production scale by anyone. Heterogeneous laser integration, manufacturing yield, thermal management. Commercial co-packaged optics deployment is projected for 2028 to 2030. That race outcome matters more for AI infrastructure in 2035. More than the 3-nanometer export control fight. America may be winning the transistor war. Whether it is fighting the right war depends on one thing. Which technology layer determines AI cluster performance in 2030? The transistor answer says yes. The interconnect answer says the question was wrong from the beginning. The companies with the best answer to that question are not in Washington. They are in Santa Clara, in Hsinchu, and apparently in Shanghai too. All of them building toward the same optical future, at different speeds, from different starting positions, with different supply chain advantages, and under very different regulatory environments. Subscribe if you want to follow where this leads. The companies shipping co-packaged optics products today are not waiting for the policy debate to conclude. Nvidia shipped Photonics networking switches in 2025. TSMC put silicon photonics into mass production. The production reality is ahead of the policy debate. The transistor battlefield was real. The controls targeting it were not wrong. They were incomplete. And the technology completing the picture is not coming from a Chinese laboratory. It is coming from Nvidia's product roadmap, from TSMC's mass production announcements, from Broadcom's 1 million link-hour test with Meta. The industry is telling the policy apparatus where the next battlefield is. The question is whether anyone is listening. Because the silicon photonics production lines are not waiting. CanSemi's 12-inch line is running. TSMC's CUBE platform is in production. The race is already underway. The finish line is 2028 to 2030. When the first commercial co-packaged optics clusters show whether light can do what copper cannot. At the scale AI infrastructure requires. At the cost that makes it viable. At the volume that determines who controls the supply chain. And leave your answer in the comments. If interconnect bandwidth becomes the binding constraint by 2030, what does the current sanctions architecture actually prevent? And the companies building the infrastructure of 2035 are not waiting for policy to catch up. They are shipping product already. The technology is real. The timeline is near. The manufacturing race has started. The policy apparatus that governs export controls was designed for a different race. Whether it can adapt before 2028 determines something important. Whether the sanctions regime still makes sense in 2030, that answer will not come from Washington. It will come from the production lines. In Hsinchu, in San Jose, and in Shanghai, the wire is dying. The industry knows it. The policy apparatus knows the wire is dying. What it does not yet know is whether the replacement is covered by the rules it wrote. By then, the production lines in Hsinchu, San Jose, and Shanghai will have been running for years. The answer is already being written. In silicon, in light. On production lines.